And we are recording. Hi, y'all. We're excited to have you here and want to welcome you to Flatiron School's Intro to Data Science, Understanding Crisp DM. My name is Corey Mickelson. I'm the Marketing Events Coordinator here at Flatiron School, and a big part of my job is hosting free introductory workshops like this evening's event to give you guys an opportunity to meet some of our instructors and get more of a feel of the Flatiron School experience. I also host a series called Tech in 20, where we take 20 minutes to discuss hot topics within the tech industry. A quick reminder, we're going to be using that chat button function as our main source of communication. So if you want to switch that little button from host and panelist to everyone, then we can all chat together. Without further ado, I'd like to introduce our host for the evening, Mark Barber. He's one of our lead data science instructors. Take it away, Mark.
Hello, thank you, Corey, and welcome everyone, and thank you for being here. So I'll share my screen here and just get into the slides. Tonight I'm going to be talking about an intro to data science through the lens of CRISP DM, and I'm going to kind of focus mostly on that. Oh, hold on here, my chat just disappeared. Do I not get chat while I'm... I might not be able to access the chat. Oh wait, here it goes. There we go. Okay. That Zoom toolbar tends to hide. So yeah, I'm going to be talking about CRISP DM, which is just kind of one process, one lens to look at the data science process through. It's definitely a little more industry standard. A little bit about me. I'm a data science instructor here with Flatiron School. I started back in October, so I'm still relatively new. But I have a background in emergency communications. I was a 911 dispatcher for about 5 years and started there while I was really young. I started when I was 19, and I really learned how powerful communication and information systems can be. I got some really great opportunities to be on like a technology selection panel while I was working there when we were doing software upgrades to our computer-aided dispatch. And that really got me interested in computers and software and inspired me to learn how to code. So I very slowly and frustratingly taught myself how to code eventually. But as I became more interested in things like computers and radios, I got a couple of IT certifications and started doing some IT consulting, first for Berkshire Hathaway for their real estate franchise out here in Phoenix. And really just kind of started, doing routine desktop maintenance and end user support. But with my programming skills, I was able to pick up a lot of other skills and move around a lot of information very efficiently, and eventually started doing pretty much everything: Wi-Fi systems, VoIP systems, AV, server maintenance, data center operations. Started working with JP Morgan Chase, specifically doing data center operations with them, and started kind of realizing where the money was and got into data science consulting. By working in real estate, I got to know a lot of local real estate brokers, and those are great people to know for business because real estate people know everybody. And once I had a couple of happy clients doing data science consulting for some real estate brokers, I just really kind of things opened up for me. And I've done just data science general consulting in computer vision, analyzing security footage for facial recognition, weapons detection, fire detection, doing photogrammetry, doing things like measuring radio towers with photos, measuring clothes with photos, kind of mentioned the security stuff, systems evaluation, looking at other models and software and data science processes that other people have built and assessing those and analyzing those. And I think so one of the questions here was why Flatiron School? Honestly, when I started data science consulting, I thought I would be doing a lot more data science, but in reality, I was just doing a lot more business. And business is a good skill to have. Everyone should definitely develop business skills, but it's not what I was happy doing. And I found myself consistently just putting stuff I wanted to learn, new kind of discoveries in the field and interesting algorithms and all that kind of nerdy stuff. I just kept putting that on the shelf and being like, well, I'll get to that eventually. I'll get to that eventually. I volunteered in education, with some local schools, a lot of like code and data literacy stuff. I really liked the vibe. I started, getting reached out to on LinkedIn to like come talk to ASU students and like Temple University and, NAU and, a bunch of stuff like that. And I don't know, I kind of like the vibe. And then I picked up another boot camp as a client and just kind of got to do a lot more data science and a lot less business. Someone from Flatiron reached out and it was a really good opportunity. And I'm really happy I made the move. It's so much less stressful and like so much more data science filled, which is great. So that's, a little bit about me. My background. I think I'm a great example of how anyone can get in this industry. You wouldn't necessarily look at like a 911 dispatcher and assume that they're going to go be doing all the things that I did in my career, but there it is. And I saw another question in here about, let's see here. I would like to know how data science can lead to different realms of work. I love this question because a lot of people that I work with and have worked with throughout my career that want to get into the industry, they think of it in terms of like, well, I'm doing this now. How do I get into data science? And I always tell them, look for the data where you're at. You all probably work in organizations that heavily rely on information flowing through their organizations and data carrying that information through that organization. If you start paying attention to stuff like that, if you start playing around with spreadsheets and maybe learn a few programming skills and start asking supervisors about information problems, things like that, and learning how to use these things to save time. Like me, I was kind of doing real estate consulting, and then that opened a lot of doors for me. I was able to prove that I could do this thing in a specific context. And the great thing about data science is it's a very generalizable skill set. It's literally the process of how we acquire knowledge from data. So any data you have, any subject matter expert access that you have, you can use these tools to help people acquire knowledge about their organizations from their data. So that's where I would say the best place to start is just learn how to program, learn some basic data literacy skills, some stats and stuff like that, and kind of focus on the data around you. The benefit of this is you're your own subject matter expert in the experiences you've had. And if you rely on the information that you already carry and learn how to analyze that information through this lens, it's going to give you a huge leg up wherever you stand in your career. So I'm very strong advocate encouraging people to learn code and data literacy skills. Let's see. Stephanie asks, can you talk about what tools you use for real estate consulting? I'm thinking about shifting my work towards this. This is going to be a good webinar for you because I'm going to do a little mock real estate analysis project. I'll spare the details, so no spoilers. I'll go over the agenda real quick. I'm going to answer the question, what is Crisp DM? I'm hoping that you all leave here knowing that answer and satisfied with it. We're going to talk about why it's useful. Why do organizations use this tool? We'll go through the parts of the process. We'll do some live coded example. There's like a Barry Bonds asterisk here. It's not really live coding because I didn't really leave any empty cells, but we'll kind of go through everything and maybe we can play around with some code and stuff. So it's not exactly live coding, but the hope here is that you guys will be able to make copies of this. I'll go through how to set everything up in Colab with you guys. And then you have your own code that you can play with and, break and mess around with and try different data sets with. So want to make sure that we're giving you something that's useful and fun to play around with and you can do some experimentation with. And then we'll wrap up with some Q&A. I'm totally comfortable kind of keeping an eye on the chat, answering questions throughout. So feel free to chime in. If I miss one of your questions, feel free to just kind of post it again. I'll probably see it, and I have Corey here to help as well. So they're gonna, hopefully call it out if I miss anything. What is CRISP DM? Well, we'll start with what it stands for, and it stands for Cross-Industry Standard Process for Data Mining. As I kind of talked about earlier, data is involved in everything these days. It's going to be hard to find an industry that doesn't rely on data in some way, shape, or form. And as a result of all this cross-industry, activity, stakeholders are finding that they needed standardized ways of communicating about data, preparing data, making it available, making it secure. There's like all these things you have to deal with when you're dealing with like server rooms full of data, right? It's kind of like how, if most people knocked a cup over, they could handle that problem. But if you like busted open a water tower, you're like you're in real trouble. You need like professionals with really big tools to solve that problem. It's no different with data. If you lost your laptop or your phone or something like that, it it might be really inconvenient for you. But if you were to try to go to log into Google and you found out that all of Google servers were down, you'd probably be running for the hills, right? Completely different scales of problem. So CRISP really kind of evolved around the development of the data industry to try to keep everyone on the same page. It's a 6-phase process. It describes the data science lifecycle. Like I said, this is just one lens, one process that models the data science process. There are others, but they're all generally the same. Awesome is another one, spelled OSEMN, and that stands for like obtain, scrub, explore. I can't remember the rest because I mostly use CRISP DM these days. But again, these are very similar ideas, right? It's just a process to go through and keep your data organized and useful so you can acquire knowledge from it and share that with your stakeholders. As you can see here, we start with the business understanding and the data understanding. This double-headed arrow here indicates that this is an iterative process. You're not going to start with an ideal business understanding. You're not going to start with an ideal data understanding. You have to, you have to kind of get into a room with your stakeholders and subject matter experts and IT professionals and kind of get everyone on the same page first. And so you're going to iterate through this process. Once you have a well-defined business problem, you're going to move on to the data preparation. And again, we have another iterative process here. You're going to do some data prep. You're going to do some modeling. You're going to get more informed about the data. You're going to probably do a little more data prep, do some more modeling, so on and so forth, until you have a practical model or reasons why you can't deliver and you need more data, more resources, more manpower, whatever you have to ask for of your stakeholder. But once you're done iterating through that, then you're going to evaluate. Typically, this is done if you are modeling. Not all CRISP DM processes require modeling. You could do just like deliver an analysis. We kind of do a little bit of both, but for purposes of time, and trying to keep it as non-technical as possible. It's a pretty light example. But you do some evaluation. This allows you to verify the veracity of your model. You don't want to just implicitly trust that you're going to dump numbers through a thing and it's going to give you accurate predictions. That can get you into a lot of trouble. So you want to take metrics, and we'll talk a little more about what that means as well. And then you kind of have two options here. Deployment, this could be a model that gets built out on AWS or Google Cloud and is accessible to stakeholders and their employees. This could be a 5-minute non-technical presentation. This could be a myriad of different things. But oftentimes you'll go from evaluation back to your business understanding. A lot of times these processes are like for static reporting and they're cyclical, right? You're responsible for looking at a bunch of data that's just constantly being logged. You're constantly looking through that data. You see this a lot in cybersecurity, trying to monitor for threats and anomalies and dangerous stuff that you don't want like sifting into your bank server room, right? So there's like iteration built into this because a lot of these processes need to persist. Sometimes it's one-off, you go straight to deployment. Sometimes you do it a few times. It's a very, very flexible model. So why do people use CRISP DM? I think I answered some of that, but more specifically, it's a process that adds structure to data science projects, and stakeholders have problems things that cost them time, things that cost them money, things that stress their labor force. They also have desires. They want to find untapped markets, new sources of revenue. They want to find more efficient supply chains, things that save them on costs. And what this process allows data professionals to do is explore relationships to find opportunities, to quantify risks and rewards of those opportunities, to find potential hazards or problems or sources of inefficiency, sometimes even to warn things, right? If you've got good static reporting and you find out a key supplier that you rely on is going to go out of business in 6 months, instead of waiting 5 months to reorder like you normally would, knowing that 6 months in advance really could have a significant advantage for you. It gives you a little bit of time to find a new one. You might be able to order up some leftover supply of what they're going out of business with and get a great deal. It's all about being informed, and you can turn hazards into benefits by really paying attention and having data professionals monitoring important things. Let's see here, just check in chat to make sure I'm not missing anyone's questions. So with the business understanding, what this looks like is primarily a lot of stand-ups, which are just very quick meetings. In the old days before the pandemic, people would literally just stand up to have a meeting to try to force things to be as quick as possible. But now that we're in Zoom's world, we are standing up by sitting down and being at our computers. And a lot of times one-on-ones, if you have a question of a subject matter expert, you are going through the data and you're not quite sure about something and you want to get their take on it, you might schedule a one-on-one with them to have have them just kind of break down a bunch of knowledge. But really what it's done is it's process that's developed between the stakeholders, the subject matter experts, and the data and IT professionals. You're going to get preliminary access to the data. This is kind of like, hey, we have this problem and here's the data that we think might assist with that. Sometimes not, sometimes that's up to you to sort out with the IT professionals. But the preliminary data is going to refer to all the relevant information needed by those on the project, right? Trying this theme of keeping everyone on the same page, keeping everyone informed as they need to be. Again, this is an iterative process. The business understanding gets refined and updated iteratively with the data understanding. And this gives your stakeholders frequent updates. And this is important because you want your stakeholders to understand what data they have access to, because it'll help them ask better and more informed questions. And this makes your job immensely easier. And the stakeholders really are, they rely on data and IT professionals to keep them informed throughout the process and about their organizations in general. So it's a role that has a lot of power and a lot of responsibility, right? Data scientists tend to be some of the most informed people in their organizations, and information is power. So with that does come a lot of responsibility. With the data understanding, the data is there to inform the questions you ask in your business problem. And it's important to remember that the data is a representation of the information relevant to that problem. It's not the information itself. There's a common expression, and it's in this industry, it's that the map is not the territory. And what does that mean, right? Well, if you go out and you find a big piece of geography and that thing exists, and you scribble down some differences, like, hey, there's a canyon over here, there's a really big tree over here, there's a hill over here, you've got these landmarks, you make a map of that territory. Well, what happens to that physical geography if you destroy that map? Well, nothing, because that geography still exists. The map is just a representation, right? And maps can get crinkled, they can get smudged, they can get torn, they can get burned, they can lose information. But that representation, even though it's gone, the thing that it represents still might be there, right? And it also might become untrustworthy. If you smudge a map and you end up taking the wrong road, well, the map is not the territory. Now you've got some problems because you trusted a representation instead of reality. And the reason why I harp this is because it's very easy to get confounded and spellbound by symbols, right? You don't want to just look at your data and implicitly trust it. You have to remember that this is just a container for information. It's a representation. It might be out of date. It might be obsolete. Someone might have transposed symbols. You might have a bad sensor. There's just an uncountable number of reasons why your data could be bad. So you always want to assume that it is bad. And you don't want to assume that it's going to make you right or correct in any way. What you're really searching for is the ability to be less wrong by provable metrics. And we'll talk a little more about what that means. But the key point here is it's important to remember that your data is a representation of the information you're working with. So you should always be a little skeptical of it. And you should always do sanity checks, always talk to your subject matter experts, always double check things with your stakeholders. It's a lot of kind of trust and communication at the human level to make sure that the computers are doing the right things and giving us meaningful results. Your data understanding is going to contain a list of features of your data. Not always. Sometimes you have like way too many features, but you'll pare that down to like a key summary. In this set, we only have 15, so they're all listed there. It's going to give you some, or you'll develop out some descriptive statistics. This gives you an idea of the behavior and the characteristics of the data. And then usually you'll do some initial exploratory data analysis. We call this EDA. And what this is, okay, I have some questions. I'm going to use this data to answer some of those basic questions and see what kind of knowledge I can acquire without really doing too much work. And this is going to orient you on what you want to do in the project and kind of what problems you need to solve. And again, this is an iterative process. You're going to revisit your business understanding. You're going to update your stakeholders. And this could change project goals. This could change timelines. It might require more data and more resources. It might refine the question entirely. If you have a stakeholder that has like a strong instinct, but they, maybe just don't have the key piece of information or the right words to express it, but, they're adamant about it. They ask a question, you get started and you find, the nerve that they were, looking for, right? And you bring that question back to them. It can save you a lot of time, save you a lot of trouble, right? But the point here is this is a very flexible and dynamic process. Change is just kind of built in as a part of it. And you're going to iterate until you have a well-defined business problem, right? So you go to between business understanding and data understanding until you have a well-defined business problem that ideally everyone can agree on. So you have a data understanding, you have a business understanding. Where do you start? What kinds of general questions are important to ask while you're building out your business problem? Well, first and foremost, what are you trying to do? Are you trying to predict a category? Is it this thing or is it this thing? Are you trying to find anomalies out of, maybe several hundreds of thousands of transactions done by a small business? Which ones of them might be fraudulent, right? It's any kind of weird event. Are you trying to predict a precise value? How many points is my team going to win by? What's the temperature going to be tomorrow at this specific time? What's the stock price going to be, right? You're trying to find some point on a continuous spectrum that will give you an answer within a reasonable range, right? Are you trying to identify groups or common patterns or trends, right? Given a photo, how many faces are in it? Can we identify all the patterns of the faces in this photo? Or if we factor analyzed a bunch of Twitter accounts, right? Are there details that we can determine about people's personalities and psychometrics and what kinds of things motivate them, what kinds of brands they follow, what kind of advertising works on them, right? So these are all kind of general data science problems that you'll bump into. And it's really helpful to be able to take like a specific problem and then decompose it into one of these more like simple general problems, because that's going to give you a starting point of, okay, I'm going to be looking at classification algorithms in the case of predicting a category, or I'm going to do regression algorithms if I'm trying to predict a precise value. What kind of data do you have to work with? Are you dealing with a lot of traditional symbols, like nominal values, ordinal values, integer values, ratio values? I'll give a little bit of details on these. It's a little technical, but I think it's really helpful for people to understand these. And it's like a core fundamental thing of understanding data types. So nominal values are things like names, labels. If you had a bag of M&Ms and you open them up and you kind of pour them out on the counter and you want to separate them by color, red, yellow, green, these are nominal values. These are like labels of things. What is red minus green? I don't know. Maybe you can get RGB values involved and do some kind of math with that, but it might not be meaningful, right? So these are just labels. These are just names. You can do things like find the most popular value with nominal values. Maybe there's way more red M&Ms than, green M&Ms or yellow M&Ms. And that brings us to ordinal values, right? You can rank things with ordinal values, but they still kind of act like nominal values. So you could say, red has the first most number of M&Ms, green has the second most, yellow has the third most, but that doesn't tell me how many more M&Ms red has than yellow, right? It just tells me the rank itself. And that's ordinal data right there. Same thing, runners in a foot race. You get first place, second place, third place, but you don't necessarily know how many feet or by how many seconds this person beat this person, right? For that, you'd need integer data. My favorite example of integer data, because it's a little tricky to distinguish integer and ratio data sometimes, but I'll give you a good litmus test. And I'll start it with a riddle. And it'll be some audience participation just to kind of get you guys warmed up for the chat. Is 100 degrees Fahrenheit twice as hot as 50 degrees Fahrenheit? Give you like 10 seconds to chime in. And don't be afraid if you're wrong. I was wrong the first time I answered this too. It's totally a gotcha. Okay. I might have given that away, but, or Heidi might be very, very smart. Anyone else have a guess? I think I might have spoiled it. But the answer is it is not. And the reason why is because 0 degrees Fahrenheit doesn't represent zero average heat in a system, right? Looking at Celsius, 0 degrees is the freezing point of water at standard temperature and pressure. There's still heat in ice. And if you wanted to find out by how much 100 degrees is hotter than 50 degrees, because you can say that they're 50 degrees apart, right? You can do that with integer data. With ratio data, you need a true zero value. So you'd have to convert Fahrenheit into Kelvin, and then you'd have to find the difference, take the ratio, and then convert it back into Fahrenheit. So that's a good like litmus test. Is think of Fahrenheit, think of Celsius, and remember that those aren't ratio data, they're integer data. And if you need ratio temperatures, you got to go with Kelvin. Another favorite example I have is really sneaky zip codes. This is a common mistake I see. People treating zip codes as integers or ratio data, but they're not. And here's the litmus test for that. If I subtract one zip code from another zip code, do I get any meaningful information? No, I don't. I don't get any distance from them. Zip code numbers don't even tell you what order they were created in time. So they're nominal values that appear to be numbers, right? And that's something to always keep in mind. You could be dealing with time series data. This is like modern witchcraft. There are so many cool things you can do with time series data. It's like, I mean, people get PhDs on this topic alone. You could be dealing with multimedia data. This is a lot of where modern big data is heading. You might not always have the convenience of nice little tables and text and symbols. You might have to deal with audio. If you're talking about these virtual assistants like Siri and Alexa, their data scientists are working on snippets of audio data, video data for, like predicting faces or anomalies in a crowd or, whatever, or identifying things in images, right? So you could be dealing with multimedia data as well. What's an example of time series? That's a great question, Andrew. So this would be things like temperature, right? You can collect a lot of previous data about temperatures from, well, probably NOAA these days is the most reliable resource, or data.gov. But, in the old days, farmers' almanacs, right? They'd track temperatures to find out when to plant things, when to harvest things, right? That's time series data. Trying to predict stock prices, right? You have a bunch of data for all stock trades. You look at a bunch of other auxiliary information and you try to predict a stock, right? So that would be an example of time series data, or like the data that's gathered at CERN, right? They smash these subatomic particles together at really, really tiny time scales, and they gather a bunch of data along that time scale. And they've discovered some pretty amazing stuff. So yeah, this is where you want to start. General questions, decomposing a specific complex problem down into something simple so that you can start making choices about what algorithms you're going to use. We won't get too much into that because it's a bit technical, and we do only have 90 minutes, and I will try to keep to as close as that as I can. It's good to be able to identify data and what you're working with. It's going to tell you mathematically what kinds of things you can do. You can't take average values of or you can't take like a mean of nominal values, right? You've got to deal with the mode, integers, ratios. Then you can start dealing with higher order statistics and things like that. Next step in data preparation. These are the fundamentals. This is stuff that you're going to have to do every time you start a project. You have to do your environment setup. This could be a Jupyter notebook. This could be a code editor like VS Code. This could be in your terminal. Tonight, we're going to be doing it in Google Colab because it kind of combines all of those tools. It's a very easy environment to set up. It's very low risk for you. You can mess up Google's computers all you want because they're like virtual and disposable. So you don't have to worry about messing up anything on your computer. It's a really great environment, and I'll share that link with you guys in a couple slides here. The next thing is you have to get all of your usable data. This could be databases, this could be APIs, this could be CSVs or spreadsheets, PDFs, Word documents. It could even be proprietary formats, especially if you're dealing with any kind of like sensor data. A lot of times you'll deal with whatever encoding the sensor maker chose to use, right? There's all kinds of different usable formats. Next, you're going to import your libraries. Someone asked a question about common tools. These would be what you want to Google and look up tutorials on YouTube for. And I can also share a bunch of playlists about like data science stuff in general. Just remind me towards the end and I'll give you guys the link. But pandas, this is a data manipulation tool. You can kind of think of this as like a really powerful invisible Excel spreadsheet. Matplotlib and Seaborn, these are visualization tools. Matplotlib is a little quicker and it's also a little more difficult to like polish up and put in a presentation. So typically when I'm using Matplotlib, it's for like quick and dirty charts that I need to interpret to do my data analysis and understand the data. If I'm going to make something for a visualization or for like a presentation or something like that, I'll probably lean on Seaborn a little more because it gives you more granular control over the cosmetic aspects of the graph. NumPy is a really great numeric and scientific computing library. And then you have scikit-learn, which is just a huge repository of machine learning models and metrics and data sets. And I mean, there's tons of stuff in scikit-learn. And the wonderful thing about all of these is they are completely free and open source, and the organizations that maintain them are pretty much propping up the entire data science industry at this point, similar to how Linux kind of like silently runs the world and no one really knows what it is. But yeah, a lot of people volunteer their time. A lot of people donate money to make sure that these tools stay reliable and they are persistent and they work fantastically, and they're shining examples of the open source community. So always hats off to these people. And then you want to work to get your data in a computable form. This is going to be a data frame, which we'll work with in a little bit here. This could be a NumPy array. This could be a data lake if you're dealing with really, really large amounts of data, like server rooms full of data. And data lakes could be all kinds of documents and collections of information. Next, in your data preparation, you want to start exploring what needs to be done before you can start to analyze. First and foremost, look at the data. Don't try to put it in a fancy tool. Don't open up a sample if it's a lot of data in like a spreadsheet, or just look at it in a text file as a CSV. And yes, I mean stare at your data. And I'll give you an example of this. This is the data we're going to be working with tonight, right? It doesn't look particularly easy to parse or whatever. I didn't say read it. You don't want to read it. You want to get an idea, you do a little bit of reading. You want to get an idea of the headers, but then just scroll through it, right? I won't do this fully here, but when I'm starting with a data set, I just literally sit and scroll and stare for like 5 or 10 minutes. And I wait for things to pop out at me, kind of like watching like a river go by, and eventually you're going to see a fish jump out and that's going to catch your eye. Maybe you'll see a plastic bag floating by. Maybe you'll see a boat going by. These are things that pop out at you and grab your attention. You would be amazed at what just blankly staring at the modern equivalent of like watching paint dry, what kinds of ideas you can derive just by, looking at the data. So I strongly encourage you to start just there, right? Just look at the data. It helps prime your brain for patterns, but it also helps orient you to better deal with abstractions, right? And computer programming and data science and statistics, this is all about leveraging abstraction. How do we take a bunch of information and compress it down into some convenient amount of information that we can process with our very limited brains? And when you actually look at the data, when you start running into these abstract problems, you have a visual cue to think back and say, okay, I know that this is kind of what this looks like. And if I do this operation, this is going to do this. And that's what I'm expecting it to do, right? Again, this gets back to like, don't trust the data implicitly, and don't trust your brain or your memory either. Look at the data, look at it frequently. If you get lost or stuck, just space out at your data and scroll it by. You'll be surprised what ideas come out. What else needs to be in your data preparation? Descriptive statistics. These are going to be counts of values. These are going to be null values and outliers. You have to make decisions about all these things. Do we have only a few null values where maybe we can take a bunch of other values in that column and we can impute that? We can kind of just like take an average somewhere and kind of populate that in. Or is half of our column missing? Well, we might have to drop that column. Or is maybe like 10% missing and we can just drop the rows relevant to that columm and still have enough data to do what we need to do. So you got to make decisions about all that stuff. Outliers, are they legitimate outliers? Meaning, was something that actually happened in reality measured within the accuracy of that tool? Or did someone transpose a digit or maybe hit an extra key or maybe a bad sensor like we were talking about earlier? This is where you're going to rely on your subject matter expertise. This is where you're going to rely on other data professionals and IT professionals if they are the ones that gathered that data or they have knowledge about it that you don't have. Maybe the stakeholders have that information, right? These are all questions. If you don't have it, you got to document them. You've got to ask people. You're looking for measures of central tendency, right? If you've got enough stuff, this is kind of what the central limit theorem says, although less proofy and way less elegant. If you've got a bunch of things, they're going to kind of converge on something, right? And this is a pattern we've seen consistently enough in reality that we kind of trust it. And so what are measures of central tendency? This is the mean, right? I have this many things, they sum to this amount, I can divide by that number of things and get a mean. What is a median? A median is when you take all the values, you order them, and you take the middle value, and that's your measure of central tendency. The difference between these is a little technical, but the main difference is that if you have a mean, they're really sensitive to really like extreme outliers. So like a common example is, if you go out to dinner with a bunch of friends and one of your buddies knows like Bill Gates and is like, hey, Bill, come join us. And you were all to sit down and compute your mean income. Bill's income is going to be really raising everybody else's income. And that measure of central tendency is not very descriptive of what like the common income is at that table, right? For that, you'd want to use the median. You order all of them up, bills would be at the top. You take the middle value. It's a little more resilient to outliers. It's a little less sensitive to outliers. And then the mode is just the most common value. Modes are something you're going to typically use on things like nominal values. And then you have value counts. And this is where, if you're looking at a bunch of data like this and we see, okay, this frame stucco here, this is a build type. What other build types are there? There's brick and block and other kinds of masonry and things like that. What value counts is going to do is it's going to tell you each unique value in a column and how many times it appears. It's very, very helpful. Let's see. So that's descriptive statistics. Again, this is an iterative process, except this time you're going to be iterating between your data prep and your modeling. You're going to acquire some knowledge about your data by doing your data prep and following these steps. You're going to do some modeling. You're going to get some more information about your data. And sometimes that's going to change what you have to do, or it's going to add some data preparation that you have to do as well. You might have to scale things. You might have to normalize things, which we won't go into today. They're a little technical for the time we have. But these are just signals for options that you have to start taking and decisions you have to start making. Then you get into the modeling. And actually, let me just make sure I'm not missing any chat. Perfect. And how are we doing on time? We started at 3, it's about 44 minutes in. Wow. This is going quick. So modeling, you're going to establish a baseline. You're going to get some quick and dirty metrics. And this is going to be the thing in which you can tell if you're improving or not, right? So that's what that baseline does for you. You're going to analyze the metrics in the context of your business understanding. So usually this is going to be like, how much variance does this model explain? And is that variance too wide for us to do anything practical with this model given our business problem? Or looking at how much error you have in the system. If it's too much error, then it might not be a very useful system. And then you have to find more data or you have to do other things. You're going to refine any data preparation as needed. Again, this is a very iterative process. You're going to consider some of the flaws of your model and think about how you can improve it. Maybe I can add another variable and that will allow me to explain more variance. Maybe I can use a different model. Maybe linear regression isn't the best thing, or you have a bunch of other algorithms to look at. And they're each going to have drawbacks and like, pros and cons with them. And that's kind of where you have to make those decisions. You're going to compare metrics between multiple models. It's really hard to interpret what like an R-square score means or an RMSE means until you start looking at multiple models and you're like, oh, this has an a higher R-square score, and this has a lower root mean square error. So this is a better model than this model. And that's really how these numbers are used. You can really understand them at a low level. You can, be a pro at this stuff. But if this stuff sounds intimidating or too technical, you don't have to worry about it. You don't need to understand it to get the general point here, because really all we use these numbers for, the context we use these numbers for is like, hey, this number is higher, so it's better. This number is lower here, so this is better. And that's kind of what guides our decisions. And then again, you iterate through this until you have some solid recommendations. Your initial metrics, we kind of talked about the R-squared score. It doesn't, initial model doesn't really tell us much, but it's for comparing models. The R-squared score closer to 1.0 is best. And the way you can think of that is an R-squared score of 1 means your model perfectly explains the data. There's no variance that the model doesn't describe. Also very unlikely to see. A lot of times if you're getting like a 0.3 or 0.4, you're really happy with that. Root mean square error, this is like word salad, right? I'll break it down. The error is, if I have a bunch of true values that I hold out for my model, and then I give it a bunch of values that I know the answers for and let it make those predictions, right? They're going to be like slightly off. They might like intersect or something like that. And then it's the differences in between those intersections, like the area under those intersections, that's going to be the error. That's how wrong your model is. If you square that error, you can get rid of negative values, which could have weird mathematical consequences. But then you sacrifice the units you're working with, right? If your mean square error is representing dollars, what does square dollars mean? I don't know. Square time is a little easier for me to conceive of, but still like not something I'm trying to do on a Thursday afternoon. So really we square this to just get rid of inconvenient negative values for mathematical purposes. Then we take the mean, right? We want the average error of our model because that's what we're trying to understand. We're trying to understand things in general. So we use a mean. And then we root it to undo the squaring so that we get back into our normal units. So now we're back into singular dollars. I'm going to try your name. Apologies if I mispronounce it. Ashutosh asks, how would one perform this sort of exploratory analysis on text or images? On images, it's a little more difficult. We'll do text as well. We'll kind of touch on some text tonight. But that I think the core of your question might be a little more kind of beyond the scope. But essentially, really what it comes down to is programming and what tools you're going to choose to use in that environment. And so basically the root mean square error tells us how off our model is. It gives us an error component. Our R-squared score tells us how much variation our model explains from that system. And, if your model is terrible, that's okay, right? I think after decades of marketing, we're so used to like 99.9% germs killed and 99.9% accurate, 99.9% everything. And, 99, like we want things to be as close to 1 or 100 as possible. But in reality, the data is what the data is, right? Your job isn't to try to get the best of anything out of it. What you're really looking for is just as much information as you can get. And sometimes that's a little thin, and that's perfectly okay to report to your stakeholders, especially if your next thing is you're going to ask them for more data or more resources or whatever, right? So it's totally okay if your model is terrible, and I'm going to prove that to you tonight. Again, iterative process. This is where you guys will have the live code here. So, and I'll actually just label this live code, or maybe I should say notebook instead of live code instead. And this is this link might look a little sketchy. This is my link shortener, so I own this domain, and I promise you I'm not doing anything sketchy with your data. If you were to get like a text message that's like, hey, click this link for blah blah, don't click on that. But in this case, you just have crisp-dm.fxbt. This is my link shortening URL for my company, Foxbat CS, and then .io is just a nice 2-letter TLD. So nice and short, nice and easy to type. When you run this, and actually I'm going to run it right now as well, just to make sure that it still works. The joys of self-hosting. There we go. Okay, so this will work. And you can see this is a public version of this. Real quick crash course, and just how are we doing on time? Okay, real quick crash course on how to use Colab. First and foremost, if you want to get a copy of this for yourself, click on File and save a copy in Drive. And it'll take a second, but then it'll open up it'll open up a new version that says copy of Intro to Data Science Crisp DM. And you can add code cells by clicking on this button. You can add text cells by clicking on this button. You can change your view settings. So if yours shows up like a bright white and it's blinding you, just go to Tools and then Settings. And you can change this under Site from theme light to dark, or maybe it's adaptive. You can change that to dark if you want. For the editor, I also recommend checking line numbers. These other boxes can be checked if you'd like, but just take the time to check show line numbers here. Again, that's going to be under Tools, Settings, under Editor, and it's just this second checkbox here. Uh-oh, I have hiccups. And that'll allow you to change that. And then with the code blocks, you can kind of enter Python and run that. It will give you an execution count here. Once it takes a second to start up while it like builds the virtual machine that it's running on. But once the first one runs, it usually runs a lot quicker. You can see now that I have a number here. That number is the execution count. So that kind of helps you keep track of what's been run. If you get any kind of error or something like that, it might be because you ran a code block out of order. So scroll through and look for empty ones that look like this. So you can see this empty square bracket, make this a little bigger. And that means you have not run that cell yet. So if I like run this, I'm gonna get a name error here. Looks really nasty and scary. Not that big of a deal. All this is telling you is that I forgot to run this code block. So super easy. If you get an error like that, just go back and check and see if you have any empty square brackets. Also, if you're clicked on a cell, it doesn't show you that information, which is kind of annoying, but I think they just presume that you want to be able to press play. So first and foremost, I'm just going to go through this really quickly, abstractly. I'll go ahead and delete this and delete this. This is a link to these slides. So this will come back here. There we go. So you can see that I've just basically laid out in Markdown this business understanding, data understanding, the business problem, data preparation, modeling, the conclusions, and my next steps. It really helps if when you start a project, you just build these things out first and foremost as like headers, and then you put in all of your Markdown and your code blocks and everything like that. So Wonderland Investments is a residential real estate developer that is completely new to the Phoenix metro area. They like to enter this hot market, but know little about building in the desert biome. And they want to select the right materials and get some basic guidelines on general features to enter the market competitively. Now, this data set was collected in like middle of last year. So real estate prices in Phoenix have just gone completely mad. I think that's a common story across America. So don't use this for any kind of actual real estate analysis. This is a very simple, as low technical thing as I could get it to be. So this is more or less to give you guys code to play around with and kind of demonstrate some of these fundamental ideas. Data understanding, the data was provided by, or the data provided was gathered through the Maricopa County Assessor's website. So this is real data. You can go out and collect this data yourself. This was collected with a tool that I wrote for when I was doing real estate analysis, which I finally got around to publishing in GitHub. So you could actually pip install this. If you're familiar with Python, you can install this library in your environment. You can email the fine people at the Maricopa County Assessor's Office, ask them for an API key. They'll be happy to give you one, and you can do all kinds of cool stuff. If you want documentation, everything like that, that's all linked here in this. So this is my library that I wrote. This is the Assessor's Office webpage. And if you go to the bottom of that page, you can get to the API documentation here. And then a copy of the data can be found here. This just links to my GitHub repo where I have the raw data. All right, so any questions, any issues getting a GitHub or a Google Colab for anyone that wanted one? Any issues accessing the link or any questions about setup before I move on? Give you guys a couple seconds here while I drink some water. Give it like 5 more seconds. But you know, if you chime in, I'll definitely get to your question. Okay, data understanding. This is where we're getting it. One thing to note, oh, there it is, September of 2021, it was not randomly sampled. The way I engineered 10,360 residential plots in Maricopa County is I just like picked like 100 neighborhoods as random as a human can be. And then I just kind of like took that neighborhood's name and like pulled all the properties in that. And I did that over and over again until I got to like 10,000 parcels. Not randomly sampled. This is terrible data, but it's something that we can at least use to demonstrate some ideas. And you could use that library. You're welcome to. This data is open source and in public domain. I just give everything away through Creative Commons. My library is the same thing. So feel free to use this stuff, gather more data. It's a lot of fun. We have our features here. These are the columns that we have. Typically, there's going to have a description. I was a little short on time. We've got 15 columns by 10,360 rows. And our business problem started with these initial questions. As I went through and built this, I came up with some more questions. So we'll start with these first. So what is the median lot and building square footage? What is the median building to lot square footage ratio, right? Given how large your house is, how big is the lot that it's on? What are the most popular building materials, right? If 10,000 homes were built in Phoenix with this, it's probably likely that it's a good material to build with. Additional questions that I came, and then what expected price point should these homes be sold for? And then the additional questions I came up with was, what is the relationship between build year and the lot size square footage and the build size square footage and the wall type and the roof type, right? There's a house that was built in the 1900s in this data set. I probably don't want to invest in building a house out of building materials that are from 120 years ago. That could be a very unprofitable venture. So getting into the data prep, I'm going to import some of my libraries. I'm going to fix this error here now that I caused. I can run this and you can see this runs just fine. Now I have this object, which is a variable that's just called df. Why df? It's a convention. You could call it whatever you want. You could call it this, and Python, as long as you consistently use it, Python knows what's up. And this statement right here, this is what's called an assignment statement. This is a very common pattern you'll see in programming, and it gets kind of touches on the abstraction I was talking about earlier. So df is the variable that's on the left. That's a container for information. This is our assignment operator. This is the equal sign. And then this is our value. This is the big, messy, complex information that we want to stick into a tiny, nice, perceivable container like df. And what this value does is it takes this URL as a string. Strings are just text in Python. It takes this URL here, points to all of this information here, and then it passes it to this read CSV method. And you can kind of think of as a method as like a verb in programming parlance, right? It's something that's going to take information and do something for you. In our case, it's going to take this information, this string with this URL that points to all this data, and it's going to put it into a pandas data frame for us. And it's going to do that by calling pandas. So we import pandas as PD. We're going to call PD. We're going to use the read CSV method. We're going to pass this link to it, and it's going to give us something that looks like this. Much, much cleaner, much easier to interpret, but you can't really see all of it at the same time. And that's why I still like scrolling through and looking at my digital paint dry. So df.head, this is another method. What this method does is it pulls the first 5 samples of your data and shows them to you. This allows you to see what kinds of data you're working with, what columns you're working with, any kind of weird stuff, any null values that you have to make decisions about. You can also look at your shape. So again, we have 10,300, and I think I said 60 before, but it's actually 390 rows by 15 columns. Null values, I'm not going to spend a lot of time here. I can see that price USD, about 40% of those are missing. Sales data, about 40% of those are missing. About 0.3% of the Latin lawn. But Latin lawn isn't somewhere we're really going to mess with today because it's not very helpful unless you have a lot of data distributed over a large area. We've got some parking type stuff missing, but the price here is really what we're worried about. We've got 10,000 some odd variables. As long as we end up with a few thousand, we'll be fine. Values. As long as we end up with a few thousand, we'll be okay. So I'm just going to do a very simple df.drop NA. So this says drop null values. In place equals true. This is just a fancy way of saying, instead of looking at this this information, I actually just want to execute it. I want to change the state of the variable df. I want to change the information that it contains to ignore all of these missing values. If we do a df shape again, we get down to about 5,847, and we're still by 15 rows. So that's our kind of data prep. Again, I'm keeping this very simple. You'd find some things, you'd iterate, you'd update your business understanding. You probably have more rigorous stakeholder problems than the ones I've laid out that require more complicated data or just larger volumes of data. Next, I'm going to do some EDA. So looking at some descriptive stats. And what df.describe does, this is another method, is it takes all of your numerical columns. It doesn't look at any categorical or text or object-based columns, just numbers, because again, you can't take a mean of a label, right? It's got to be numeric. Zip codes will trick you up here. So just they will end up in here, but you can't really do any kind of meaningful descriptive statistics with zip codes. So that's a common trap for people. But I noticed something annoying here. I have this +3, +5, +5, +4. This is scientific notation. If you want to get rid of that, this is what you would Google to get to this article, the Stack Overflow article, which will ultimately lead you to this solution. This is just calling pandas. It's looking at the options, the display, and the float format. This looks like, really confusing or whatever. I don't bother to parse this. If I need to use this, I just go look it up every time. But what this is saying is just go to 2 significant figures only. Like it's making this a format object. So now when we run .describe again, that scientific notation goes away and we have a nice .00, .29, something that looks a little more like US dollars. People don't spend money in scientific notation. So we're kind of set up here, just analyzing this. We see the count of our values, right? I can anchor this with the shape and kind of use that as a sanity check to make sure that, I'm still dealing with the same information. We've got the mean. So the mean lot size is 9,800 square feet, actually almost 9,900 square feet. The mean price is 395,000. Again, this is over 120 years. This might not be very useful information. Standard deviation, the minimum, the maximum. You have interquartile data here, all kind of useful stuff. And the 50% here, this is the median. So you have even though it doesn't say that, you have the mean and you have the median as well. And when you see a difference in your mean and your median, that means you have skewed data. I'll let you guys Google that and watch some YouTube videos about what to do about that. What is the median lot and building square footage for the data, right? We're starting to get into our stakeholder questions. Andrew asked, how did I fix the name error? So when I first created it, I didn't run this cell. I just ran this one and that's what created the name error. And then I went back and ran this and then ran this again and that should have fixed it. So if you get that, let me just generate, oops. So I'll just say, hello, this is a variable that doesn't exist. I'm going to get a name error by calling it. If you get something like this, just scroll up and see if you have any missing, like any empty square brackets. That means you just might not have run something that came before. If you run it and try to run through everything again, it should fix that. Nice. All righty. Let's see here. And I noticed that some of these I didn't run either. I've just been relying on what's shown up there. All right. Got this. Okay, we're in business. Okay, so what is the median lot and building square footage for this data? We kind of already saw it up here at 7,009, but we have it kind of separated out, easy to see. This is the building size median. And what's the square footage ratio? It's about 0.27%, right? So all I'm doing is I'm taking every value in df.build size. So if I look at that, it's just a long series of numbers and I'm taking the median of that. So if I look at that value, that's basically what we have up here. And then I'm going to divide it by, again, a very long series of numbers that corresponds to the lot square footage. How am I doing on time? Oof, might be a little close. Again, a long series of numbers, and we're just taking the median and we're dividing one value by another value, and we get to about 27.4%, right? So a little more than a quarter of the lot size is the average build size. Again, it's important to remember, this doesn't necessarily represent all homes in Phoenix. This represents 10,000 non-randomly sampled homes. So we do not trust this data. But according to this data, all of it says it's about 0.27 is the median build size to lot size ratio. Obviously, you would expect that. You typically don't have a building larger than the lot that you're building it on. New question. What is the relationship between build year and lot size square footage and build size square footage? So this graph, so I've done df.groupby. Groupby is another method that allows you to pick a column and then group things up according to that column. So it'll go through each column and find, so if I do like a df.head here, it's going to go through each one of these build years and it's going to say, oh, okay, 2007, that's a new bucket. Hey, look, 2007 again. These two values are now going to be in that bucket. And another 2007, these three values are going to be in that bucket. Let's pretend this is 2008 for purposes of demonstration. Hey, this is a new bucket. Now this value goes in that bucket, right? You're just grouping things up by each specific year that you have. The data runs from 1900 to 2021. So you got 121 years there. It's just going to bucket things up for you. And then we're going to look at the build size square footage. So it's going to take all of the build size square footages in 2007. It's going to order them, take the middle value. And that's what we're doing here with the median, right? So we've grouped our data by year. We've taken all of the build sizes for each year and taken the median values for each of those years. And then we've plotted it as a line chart. We've added a title called median build size in square footage by build year, with an X label of build year and a Y label of build size in square footage. And maybe I can, hold on here, make this a little bigger. Maybe not. Yeah. Okay. So what we have here is from 1900 to 2021-ish. We see a lot of noisy data, right? I mean, I know the 20s through the 40s and maybe even the 50s are pretty turbulent times in the world. But I have no idea what this is. And on top of that, we kind of touched on the issue. I don't want to be building stuff that they were using 100 years ago, right? I want to look at more modern stuff. So that's kind of one intuitive decision we're going to start to make. Let's take a look at the lot size. Same kind of thing. We've just got this like whatever data catastrophe here for these values. And then we kind of see things even out. Things get a little hairy in the 80s, and then we get back to like a slow decline in lot sizes. Since the data for all years is very noisy, we're just going to cap our data back to 20 years. We're going to look at more modern homes only. This also excludes that giant messy peak that we see. Again, this could be results of events that actually occurred during those decades. It could also just be an artifact from the data gathering methodology or lack thereof that I used. This data is not randomly sampled, like I mentioned. So I'm going to assume that it's an artifact from the data gathering. And I just happened to like pick a neighborhood that had like these really large homes, and I don't know, maybe they were like farm, I don't know, who knows, right? But probably just an error from the data gathering. And I'm going to drop those everything to the last 20 years. So df.groupby, build year, build size, square footage. I'm going to take the median, just like .head gives you the first handful of samples, .tail gives you the last handful of samples, and you can give it an integer, and that tells you exactly how many you want. So if we look at this, we've got the build year from 2002 to 2021, and then we have the median square footage for that year. And just by looking at this, we can see it kind of trend up, and then the financial crisis happened and things got a little smaller and things started doing better and houses started getting bigger again. And now they're kind of like on a downward trend, right? But let's kind of commit to this past 20, right? We see much less noise in this data. So we're going to save it for a variable, or save it as a variable, and kind of work from there. So the way I'm going to do that, I'm going to create a variable called past 20 df. I'm going to assign it the value of the data frame, where inside of that data frame, I want to look at the build year that's greater than or equal to 2002. So this is just a logical test. If I were to run this, what you would get is a very confusing looking series of, oh, actually, hold on here. This is what I want to do. You get this very confusing series of true and false values. This is what's called a Boolean mask. And what this is going to do, like we saw here, is it's only going to give you the values where this statement evaluates as true. So it's going to go through each of these build years and it's going to say, hey, is this greater than or equal to 2002? False, rejected. Is this greater than 2002, greater than or equal to 2002? True, keep it in. And that's why all of these values are greater than 2002 here. So we basically just junked the first however many years of our data frame so we can look at more meaningful, more modern data. So that's what this does. And now we see that we're down to 2,484 samples, still okay. We're going to look at the head here, just like we looked at above. Let's see, any questions? Good to go. The median build size for residential home in the past 20 years is 2,096. We'll call that about 2,100. And if we compare this to the past, we see that this is about 9% larger than homes in the entire data set, right? The median lot size for residential homes is actually a little smaller. It's about 5% smaller. So for just these past 20 years, it's about 6,600 square feet. And if you divide that number by the number that we get for all of the values in the data frame, it's about 5% smaller. So based on this, there is a change going forward. We're only going to explore past 20 DF. We're going to look at the build size square footage to lot size square footage ratio for this data frame, and it's about 32%. So this means that we want our floor plans to be roughly about 1/3 of the square footage of the lot. What are the most popular building materials in past 20 DF? Again, we just want to focus on this. We don't have to look at the entire data set. So for the wall type, I'm going to call my data frame. I'm going to refer to the wall type variable. And one thing I just want to call out here, there's actually two ways of referring to a column. As long as your column name is something that's like Python parsable as a variable, you can use this dot notation. So you've probably seen both ways. And the reason why I mention it is if you see this in the wild, don't be confused by it. It's just a different notation that allows you to do different things. So you can use either of these and that's fine. In both cases, they just refer to that specific column on that specific data frame. And I'm going to do dot value counts. Kind of talked about, whoopsie, what did I do here? Oh, yes, I've not been running my cells. So for those of you who've got name errors, this is how you fix that. So that was the last one I ran. I'll run this, I'll run this, I'll run this, and this. Just kind of run everything until you get these green check marks here. Run that again, and that'll fix that. So again, the value counts takes all of the unique values in that column, and it gives you a count of how many times that column appears. So we see frame stucco is about 1,300 of the homes that we have left. Frame wood is about 1,084. Again, we're dealing with only 2,400 values now. And then we have 8-inch stucco and 8-inch painted block. And we've got some other stuff that, it really rapidly dwindles here. After doing some minor research, there isn't really a difference between frame stucco and frame wood in terms of construction. Both are built from wooden frames, and stucco is just one type of exterior finish. It's also applied to block and other masonry. So that's what the 8-inch stucco that's talking about 8-inch masonry bricks, and then 8-inch painted block, same brick, different cosmetic covering. So really the build material here is whether it's going to be a wooden structure or a block structure. As we can see, wood is far more common. Stucco is still pretty significantly more popular. So that's going to be the build material that I'm going to recommend. And then let's see here. This is this might be something that you would call out. Let's see here. Oh yeah, so there could be many reasons for this. That might be cost, durability, repairability. We don't know. If we need further information, we might want to pin this to say, hey, let's talk to a subject matter expert and in construction or contracting or supply chain to get more information. Let me see here. Okay. Okay, so we got the value counts for the wall type. We got the value counts for the roof type. Concrete tile seems to be the way to go, right? We're already kind of answering a lot of these questions. We have an idea of how big we want our houses to be. We have an idea of how big we want the lots to be. We have a good idea of the wall type and the roof type. There's some more details in here I'll let you read. I just want to be cautious about time. What other strong relationships exist in past 20 DF? This is where we would use a Pearson correlation, and I'll kind of show you how to use this real quick. I want to make sure that I leave time for Q&A though. So basically what I'm doing here is I'm plotting a figure. I'm setting the size to 12 by 12. I'm using Seaborn and I'm using the heat map method. So remember, Seaborn is just a visualization library. I want a heat map that takes the correlation of all of the data in the past 20 DF. And so this is what's called a pairwise correlation, also called a Pearson correlation. It just takes all of the data and compares it with every other column, right? So you kind of get this like intersection. So you can see where lot size square footage intersects with itself. We have a 1, where price USD intersects with itself. We have a 1, latitude, longitude. We have this like diagonal 1 down here. That means you can just ignore half of the upper or lower, right? This is also really terrible to look at. And that's why we pass this code that generates this up here. We're passing this to this method and we're telling it some cosmetic information. We want the line widths to be 0.25. We want these to be square. We want the color map to be seismic, which is this kind of like red, white, and blue, like heat map type of thing. We want the line color to be black. K represents black. And we want annotations to be true. That's just these little numbers here. So now this is much easier to look at. I can immediately see if we're talking about price points, that build size square footage is the strongest correlation with price USD at 0.65. There's other pretty strong candidates as well, but we'll start with linear regression. Parking is another thing to consider, but pretty much all of these homes in the past 20 years have garages. Very few of them have covered parking, so we would recommend that they build a garage. Next, we're going to train, test, split. I don't know if I'm going to finish. Let's see here. Yeah. Sorry, guys. All right, I'll make this a little more abstract. We train, test, split our data so that what I was talking about earlier, we have enough information to actually train our model, but we're going to hold back about 25% of our values, which is what this test size is. And think of it as like the answer key to a test, right? We're going to train our model, then we're going to give it the X values from the holdout data and have it give us back the predictions. And then we're going to compare its predictions with the true values that we know. And that's how we're going to be able to tell like where that error is, like how far off our model is. That's how we know we can trust it or not trust it more specifically. So that's what all the syntax here is. I encourage you to play around with this, Google things, reach out to me on LinkedIn if you have questions. I'd be happy to go over it. So we've split our data up so that we can actually test the veracity of our model. We're going to set a baseline model, which is just simple linear regression. I'm going to import NumPy to do some number handling, and then I'm going to use scikit-learn to import the linear regression model and the root mean square, or the mean square error, which has an option to make it the root mean square error. I'm just going to give it the build input size of 2100. I'm going to train the model, or rather fit it in linear regression's case. And then I'm just going to print out, and this all looks very complicated. All I'm doing here, these are labels that I'm just adding in to make it look pretty. This is the core of the code in this line. I'm taking my linear regression model stored in the variable reg. I'm using the score, which gives me the R square score. I'm passing in my feature matrix. I'm passing in my my target, and then I'm making a prediction, right? And my R square score here is 42%, not bad. My prediction is $300,000. Okay, seems reasonable, especially not accounting for 2022. Now, let's actually evaluate this, right? If we go through and take the root mean square error, we can see that our model is off by $331,000. Do we trust this model? No, we do not, because what this says is, hey, I'm going to tell you to price your homes at $300,000, give or take $330,000. Not very helpful, right? And that's why we do things like this. Because if we were to just run this number through here and be like, yep, 300,000, you're good to go, we might get some very angry calls from people. So we always check our metrics. We can do multiple linear regression by adding in another variable, in this case, lot size. Got a lot of multicollinearity and a bunch of technical stuff wrong with this, but we add it in anyway. We don't want to assume that because we're adding more information, our model gets better. Case in point, the root mean square error, when we add in the lot size, it's actually 395,000. It's even worse. So be cautious with this stuff. The problem here is multicollinearity. If we look at this Pearson correlation, we can see that price USD and build size are strongly correlated at 0.65. But if we go down build size to lot size square footage, they're correlated at 0.66. So what that means is they're doubling up on how much of this system the model explains, and that's bad. We want to avoid that. There's a bunch of technical stuff we can do to fix that, which is kind of beyond scope and a little past time. But this is kind of what the process looks like. You set a baseline. Anything that's worse than that, you can safely ignore. Anything that's better than that, you want to pay attention to. You add in your conclusion, just real quick, we'll compare these. So if we just look at the multiple linear regression and the linear regression R-squared score, we actually see that this improves, right? But because our root mean square error got so much worse, the little bit of, the few percentage points of extra variance explained really doesn't do anything for us. So on the grounds of the root mean square error, how much our model is off by, we're going to trash the multiple linear regression model and just stick with the simple linear regression one. And here are our conclusions. The home characteristics, based on preliminary analysis of the data, we recommend building homes with the following features: 2,100 square foot build size, 6,700 square foot lot, attached garage, frame stucco wall type, concrete tile roof. Price recommendations, they kind of want to look, I think somewhere in here I had them fictitiously wanting like 10% below and above size of homes and see what those price points are. So I go through that whole thing. And assuming we want to trust this data, again, these are preliminary results. We'd want to charge like 210,000 for like a 1,900 square foot home, 300,000 for 2,100 square foot home, and 390,000 for a 2,300 square foot home. If you want different results, which I encourage you to actually want, then you have to give me more data, and I can go through this again, stakeholder, blah, 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 right? This is what helps you prove that the data you have to work with so far is not good enough to answer your stakeholders' concerns. You talk about the limitations due to poor performance of the initial modeling. We recommend proceeding with next steps before committing to any purchasing decisions. Additionally, many factors could change depending on the location of the lots purchased for developments. Next steps: gather additional samples randomly, include a greater number of features for each home, gather data on a more frequent basis to capture trends over time, right? Get some of that tasty time series data, meet with a supply chain subject matter expert to get a better idea of costs, run this analysis on several candidate development lots so we can target in on a specific piece of real estate and do this analysis again. So that's a very, very quick kind of fictitious example of what this stuff looks like. You kind of saw a very light iterative process. We saw a little bit of evaluation where we took our testing data and we kind of tested our model to see how well it does. And in this case, deployment, really we'd be going back to the business understanding and the data understanding, acquiring more stuff and iterating through this process till we had something high veracity and reliable to work with. And deployment for this project might look like a combination of the following: generating reports for candidate lots, right? Just large PDFs with a bunch of information, deploying a pricing model. Sorry about that. I thought hold on. Apologies. This could be deploying a pricing model for our stakeholders to use on a cloud service like Google Cloud or AWS, or creating a non-technical 5-minute presentation for potential investors, right? Deliverables could mean a lot of things. You got to be very flexible. Okay, so with that Q&A, we made it with 7 minutes to spare. And I'll go ahead and stop sharing my screen and make sure I didn't miss any questions. I'll try to pronounce your name. If I mispronounce it, apologies. Is it Subash? Thank you for the feedback. The session will be recorded. I think Corey mentioned she's going to send that out. Is it like 2 or 3 days?
It'll be out in the next 3 business days. Everybody that registered through the event will get a copy of the video. We also have our YouTube page where we post all of our workshops, and you will get the assignment with the websites and the slide deck.
And I can also...
And then Mark dropped it in the chat one more time. If you guys want to save that, that's also what I'm going to be sending to you.
And that first one is my LinkedIn. Feel free to connect with me on there. I'm always happy to share resources and information. I also mentioned some YouTube playlists. So if you go to my YouTube channel, a lot of that isn't my content. It's just stuff that I've like accumulated over the years that's helped me and has had really good explanations. And I've just kind of like compiled it over like a decade of learning. And along the way, some people asked me to share it, and I'm like, yeah, why not? So if you go to yt.foxbetscs.com, it'll just redirect you to my YouTube playlist page. And I've got a ton of playlists about data science and Python and information theory, just tons of really, really great channels. I highly recommend Art of the Problem, MIT OpenCourseware. Absolutely. Those are great sources of learning. So yeah.
Looks like we do have a question. How do data scientists interact with software engineers? They're enrolled in a software engineer program, but are fascinated by data.
Yeah, that's a big question. As a data scientist, you might not interact with software engineers at all. If you're working at like a big like FANG company, it depends on your role. If you're probably in a higher project management status as a data scientist, you might interact with software engineers. As a software engineer, you might get on a team for a data science project. They might have a deliverable that's like a front end or a client facing tool that they need software engineers to build out. So if you're interested in data, depending on where you're working, keep an eye out for those opportunities and kind of volunteer. And if you develop some of these skills and can show those off, it's a good way to get into the industry.
And I just put in the chat, there's our official YouTube channel if you want to go there and subscribe. There's our website for all of our future and upcoming events. And then there is a chance to make a 10-minute chat with our admissions team if you want to learn more about the program. Do we have any more questions tonight?
Yeah, Fred asks, what about a startup that has both? Oh yeah, it's definitely possible. Companies, especially, software companies and things like that, you'll very likely have both. I think a lot of modern companies are realizing that they need data people, just like 20 years ago everyone needed IT people. It's just like the next iteration of technology. So if you are working at a software company that employs software engineers, even if they're a startup, it's pretty likely that they'll either want a data scientist or have data scientists already. Absolutely. Great question. Thanks for asking.
Okay. Oop, there we go.
Andrew asks, is what we just went over comparable to a project we would create during the course? Maybe a little more rigorous. This is very, I had a 90-minute slot, and as you can see, it was very close to capacity on that. And it was a struggle to try to keep things concise and less technical, but also just kind of fill the appropriate amount of space. So this is, it's a good representation, but you would definitely do a little more rigorous of a project. You'd also have like a full week to do that. If you're in the live program, if you're flex, well, I'm not a flex instructor, so I'm not sure. I would defer to Corey's knowledge. But I think that's kind of like, code as you go type of thing.
Awesome. Thank you everyone for coming. I wanted to thank Mark and everybody else who zoomed in and joined us tonight. If you have any further questions about Flatiron School, I dropped the links to schedule a chat with the admissions team. And as a reminder, you're going to receive a copy of tonight's presentation within 3 business days. And if you'd like to see our previous events, go ahead and subscribe to our YouTube channel. Thank you all. Have a great night. Bye.